Today we're going to start talking about steady state sinusoidal circuit analysis. And I am going to try to make up some time because we missed that day because of the weather a week or so ago. And also because a lot of this is review from circuits one, I feel like I can go through this relatively quickly. And if there's anything that we need more time on, you guys tell me and we'll make that. So without any particular derivation or anything, because all of that is handled in circuits one usually, we know or should know at this point that if we have a sinusoidally varying voltage signal of the form Vm cosine omega t plus theta v, we can express this signal in the frequency domain as a phasor simply by keeping the magnitude, keeping the phase angle, and suppressing our frequency dependence, right? And we can do the exact same thing for a current. So if we have a current Im cosine omega t plus theta I, then this would look like some phasor current I is equal to Im angle theta I. The reason that we're able to do this is because our voltage waveform V of t is nothing more than the real part of the following exponential number, Vm e to the j omega t plus theta v, which is what I like to call the mixed domain representation of that voltage signal. And similarly, I of t is the real part of the complex number Im e to the j omega t plus theta I. So we're going to use these exponential form complex numbers to develop frequency domain relationships for all of our circuit elements. Again, this should be review from circuits one. So for a resistor, so let's say that we have some generic resistance R, like so, where there is a time domain voltage drop across it and a time domain current flowing through it. And I'm going to use the V of t and I of t from up above. We know that V of t should simply be R times I of t, which is nothing more than Ohm's law, right? So if I substitute in my complex number expression for my voltage and current, what this is going to look like is Vm e to the j omega t plus theta v is equal to R times Im e to the j omega t plus theta I. I can split each of those exponential functions up because I have an exponential of something plus something that's going to look like the exponential of the first thing times the exponential of the second thing. So we would have Vm e to the j omega t times e to the j theta v is equal to R Im e to the j omega t e to the j theta I. We can very easily see that there is a common factor of e to the j omega t on both sides, which goes away. That's me suppressing the frequency dependence of this relationship, which is effectively all I'm doing up here when I'm giving my phasors. I'm just saying, hey, the omega t bit doesn't really matter. We just keep track of our magnitude and phase angle. So similar thing, different application. So I want us to observe a couple of things from looking at this relationship. We're going to make observations like this for every one of our circuit elements, okay? So on the left-hand side, I have an exponential form complex number that has a magnitude of Vm and a phase angle of theta V. And on the right-hand side, I have another complex form exponential number that has a magnitude of R times Im and a phase angle of theta I. So if I have an exponential form complex number on both sides of the equal sign, it means the magnitude on the left has to equal the magnitude on the right, and the phase angle on the left has to equal the phase angle on the right. And from this, we can say that the magnitude of our voltage Vm is simply going to be R times the magnitude of our current. And we can say that the phase angle on the left-hand side, theta V, has to be equal to the phase angle on the right-hand side, theta I. Okay. So this is governing how the magnitudes behave and the phase angles behave when we have a pure resistor. Now, going a little bit further, we have Vm e to the j theta V is equal to R times Im e to the j theta I. Well, Vm e to the j theta V can be expressed using polar form. So we would just have Vm angle theta V. And over here, we would have R times Im angle theta I, with the understanding that Vm angle theta V is nothing more than our phasor voltage, and Im angle theta I is nothing more than our phasor current. This gives us V phasor is equal to R times I phasor, and therefore Ohm's law looks just like Ohm's law, even if we're in the frequency domain. Now let's look at what's going on with an inductor. So let's say that I have some generic inductance L, across which I have sinusoidally varying voltage V of t, and through which I have a sinusoidally varying current I of t. We should know that the voltage drop across an inductor is given by L times the derivative of the inductor current with respect to time. So if we substitute in our complex number relationships into this expression, what we wind up seeing is Vm e to the j omega t plus theta V is equal to L times the derivative with respect to time of Im e to the j omega t plus theta I. So if I perform that derivative, the Im is a constant, so it's going to come out. So the derivative of e to the j omega t plus theta I is just going to be j omega e to the j omega t plus theta I. And so that winds up giving me j omega L Im e to the j omega t plus theta I. So taking a derivative in the time domain is effectively just multiplying by j omega in the frequency domain. Okay. Once again, I can split these up just like I did previously. And so now I'll have j omega L, that L looks garbage, e to the j omega t, e to the j theta I. Suppressing my frequency term on both sides, I have this relationship. And I'm going to take this one step further and let me know if you need me to explain what's going on here. But I'm going to move this j inside my exponential function. So that's going to look like omega L times, oh, and I missed the Im there. Sorry about that. Let me sneak that in. Im e to the j theta I plus 90 degrees. Expressing the right-hand side of our equation in this way lets me see specifically that the magnitude of my voltage, Vm, is equal to the magnitude of the right-hand side, omega L times Im. And it also lets me see that my phase angle, theta V, is simply theta I plus 90 degrees. So that means that the phase angle of the voltage is always 90 degrees more positive than the phase angle of the current. And another way that we like to express this is by saying that in an inductor, the current lags the voltage by exactly 90 degrees. So from here, we have Vm e to the j theta v is equal to j omega L times Im e to the j theta I. Looks like phasor voltage V is equal to j omega L times phasor current I, where we skipped this intermediate step this time. So anytime we see it of this form, we're just going to go directly to the phasor representation. All right. And then lastly, we have capacitors. So for our generic capacitance C, where we have some voltage across it V of t and some current flowing through it, I of t, we know that capacitor current is C times the derivative of the voltage drop across the capacitor. And thus, Im e to the j omega t e to the j theta v, just skipping ahead here, is going to be, C times the derivative with respect to time of Vm e to the j omega t e to the j theta v. Damn it, this should have been a theta I. Apparently I should have slept a little bit longer. And this is going to give me j omega c Vm e to the j omega t e to the j theta v, where this guy and this guy cancel each other out. Once again, I can move that j from out in front into my phase angle by simply adding 90 degrees. So that's going to look like omega c Vm e to the j theta v plus 90 degrees. And therefore, the magnitude of my current Im is simply omega c times Vm. The phase angle of my current is theta v plus 90 degrees. And now we see that for a capacitor, the current always leads the voltage by exactly 90 degrees. So from here, we have Im e to the j theta I is equal to j omega c Vm e to the j theta v, or phasor current I is equal to j omega c times phasor voltage V. So before we move on to the concept of impedance and admittance, does anybody have any questions about this? Hopefully it was all review. I know it was all review if you took me for circuits 1. So sorry for the half of you guys that are bored to tears currently. It's not going to get any better for the rest of this class meeting. All right. So impedances. So in a DC circuit, let me draw a little diagram here. If we excited a DC circuit, doesn't matter if we excited it with a voltage or a current. This is our network under test. This voltage V here is a voltage that we could measure using a multimeter if we were to excite this network. And this current I is a current that we could also measure with a multimeter or an ammeter. And what we found was that the resistance of the network under test was simply the ratio of the measured voltage to the measured current. Well, in an AC network, we can do something similar. So if we excite our network with a sinusoidal source, doesn't matter if it's a voltage or current, and we measure the phasor voltage across the network and the phasor current flowing into the network, we can define impedance Z as simply the ratio of phasor voltage to phasor current. Because Z is a ratio of two complex numbers, it must also be a complex number. So that means that we could express it in polar form or rectangular form. So let's look at polar form first. So this is going to be Vm angle theta V divided by Im angle theta I. And knowing how to manipulate complex numbers, this gives us the ratio of Vm over Im with an angle of theta V minus theta I. And now we have some distinct magnitude, which is just Vm over Im, and a distinct phase angle, which is theta V minus theta I. So our rectangular form has a magnitude that's just the ratio of the voltage magnitude to the current magnitude, and it has a phase angle, which is just the difference between the voltage phase angle and the current phase angle. Okay? No special names or anything like that right here. Now in rectangular form, we can express our complex numbers with a real part and an imaginary part. Okay? So we might have it expressed as R plus JX, where R is what's known as the resistance, analogous to the resistance that we are used to. And then X is what's called the reactance. And this is simply the imaginary part of Z. And our resistance is the real part of our impedance, Z. So we can transform back and forth between our polar form representation and our rectangular form representation just by doing simple complex number manipulation. So for example, the magnitude of our polar form is simply the square root of our real part squared plus our imaginary part squared. The phase angle is just the inverse tangent of the imaginary part over the real part. And going from polar form to rectangular form, we know that our real part, the resistance, should just be our magnitude times the cosine of theta z. And our reactance should be the magnitude of z times the sine of theta z. Where all of those relationships just come from simple complex number manipulation. So if we looked at a resistance, the impedance of a resistance is just the ratio of phasor voltage V to phasor current I, and that simply comes out to be the resistance value R, right? Expressed as a rectangular form complex number, this looks like R plus J0, and expressed as a polar form complex number, this looks like R angle 0 degrees, where we have some units that will simply be in, obviously, ohms. Okay. For an inductor, we take the ratio of phasor current V to phasor current I. We get simply J omega L, which can be expressed in rectangular form as 0 plus J omega L, or omega L with an angle of positive 90 degrees. So if we look at the units here, we have omega, which is measured in radians per second, where a radian is a dimensionless quantity, and then inductance is measured in henries, where a henry is a volt second per ampere. So radians are going to go away effectively because they don't mean anything. Seconds gets canceled by seconds, and we have volts per amp, which is just a fancy word for ohm. So quite obviously, the units of impedance for inductors are also in ohms. And then lastly, for a capacitor, we would have 1 over j omega c, which could be more formally expressed as 0 minus j divided by omega c, where I'm simply using the identity that 1 over j is the same thing as negative j. And so this is going to look like 1 over omega c with an angle of minus 90 degrees. And looking at the units, we have 1 over radians, so that's seconds per radian, times 1 over capacitance, where capacitance is measured in amp seconds per volt. And once again, we can see the radians goes away because it's a dimensionless quantity. Seconds cancel seconds, and we have volts per amp, which is also simply ohms. Since all of our impedances are measured in ohms, effectively we can combine impedances just like we combine resistances in circuits one. So nothing particularly wild or crazy there. All right, so let's talk about something arguably new. So I'm going to come back up to this diagram right here. So in a DC network, we define the resistance to be the ratio of the voltage divided by the current, right? Well, you could also define a ratio of the current divided by the voltage as what's called conductance, right? Well, there is an AC equivalent of conductance, what is called admittance, where admittance is simply the ratio of phasor current divided by phasor voltage. Okay? So admittance Y is defined to be phasor current I divided by phasor voltage V. So that means we would have IM angle theta I over VM angle theta V. And this would be IM over VM angle theta I minus theta V, which would simply be the magnitude of our admittance Y angle the phase angle of our admittance Y. But we can relate this to our impedance as well, right? So the ratio of IM over VM is nothing more than the inverse of the magnitude of our impedance. Because impedance is VM over IM. And then our angle theta I minus theta V is nothing more than the negative of the angle of our impedance. So this is literally nothing more than 1 over Z. So that's what we have in polar form. In rectangular form, Y can be broken up into its real part and its imaginary part, where the real part of admittance is called conductance. And the imaginary part of admittance is called susceptance. And hopefully, obviously, we can go back and forth between the real parts, or excuse me, between the polar form and the rectangular form, much like we did earlier. So the magnitude of Y is just going to be the square root of G squared plus B squared. The phase angle of Y is just going to be the inverse tangent of B over G. G is just going to be the magnitude of Y cosine theta Y, and B will just be the magnitude of Y sine theta Y. And we can actually go back and forth between impedance and admittance. So for example, we could express the conductance G as R over R squared plus X squared. I'm going to point something out here. This is not equal to simply 1 over R like we saw in DC circuits. So it has a slightly different meaning here in the context of an AC circuit. Our susceptance B is going to be negative X over R squared plus X squared. Going in the other direction, we could say that our resistance R is going to be G over G squared plus B squared, which should be kind of obvious, is not equal to 1 over G like we would have in DC circuits. And then lastly, our reactance X is negative B over G squared plus B squared. The admittance of a resistor by itself is simply 1 over R or G. So this would be expressed as G plus J0 or actually, let me do it like this. 1 over R plus J0 or 1 over R angle 0 degrees with units of the inverse of an ohm. We know that that's usually called a Siemens, but I'm going to leave it as inverse ohms just because that's the habit that I've developed. The impedance of, excuse me, the admittance of an inductor is 1 over J omega L. So that would be negative J over, actually, excuse me, 0 minus J over omega L, or 1 over omega L angle negative 90 degrees, once again measured in per ohms. And lastly, the admittance of a capacitor is J omega C, or 0 plus J omega C, or omega C angle positive 90 degrees, measured in per ohms. All right, so, oh, I guess one last thing here. Since all of these admittances have units of per ohms, they would combine effectively like conductances do. We don't really cover how conductances combine in circuits one, so just treat them like they were capacitors effectively. So they can combine like capacitors do. All right, so I've hit you guys with impedance, which we're going to use a whole heck of a lot in this class, and I hit you guys with admittance, which we are probably never going to talk about again in the context of this class. However, when we get into our junior level classes, particularly when we're dealing with circuit analysis in the Laplace domain, which will be circuits 3 for hopefully all of you guys in the fall, we will start using admittances much more, and we will definitely do it when we get into our electronics courses, because we're going to see that the way that things shake out, we're constantly going to be having like 1 over resistances and all of that kind of good stuff. And so just using conductances and admittances will make the math way, way easier. So for right now, it's just kind of, here's what it is, and then we're not going to look at it again for like 6 months. So just wanted to make you aware of it. Okay. So that is all the material that I wanted to cover today according to the syllabus. That being said, I am trying to catch up. So what we're going to do now is we're going to introduce frequency analysis, or excuse me, circuit analysis in the frequency domain. So I understand fully that you guys have been exposed to all of this material before because it was the last third of circuits 1. What I want to know from you guys in particular is what parts didn't make sense to you? Like, what do you need a review on? With the understanding that we are definitely going to cover complex power and all of that kind of stuff in a couple of days. So I already understand that you guys don't get that super well because we covered it so quickly back in circuits 1. We'll spend some time on it in here. But just from an analysis standpoint, what do you guys want to look at? All right, well, nobody's saying anything, so I'm just going to make stuff up. So let's say that I have the following network where Vs of t is equal to, let's say, 12 cosine 15T volts. And I want us to find the time domain Thevenin equivalent circuit. So what do you guys think a time domain Thevenin equivalent circuit might look like, given your prior understanding of Thevenin equivalent circuits? So a Thevenin equivalent circuit, by definition, will be a Thevenin voltage. Since we're in the time domain, it's going to be a time varying voltage. And then usually it would be connected in series with some resistance, right? If we're looking at a DC network. Well, we're looking at an AC network that's composed of resistances and an inductance. So I am going to posit that we should probably have some resistance R-Thev in series with some inductance L-Thev. Now, I'm like 99% it's going to wind up looking like an inductance. Actually, I'm 100% sure it's going to look like an inductance, but you might not understand why just yet. So let's put a pin in this thing here and we'll sort out whether it's actually an inductance or maybe a capacitance here in a minute. It'll be an inductance anyway. All right, so how are we going to find our Thevenin voltage? How do we find the Thevenin voltage in a DC circuit? What is the definition of a Thevenin voltage? So say that again, please, so I can tell you you're wrong. Yes. Sorry. So find the open circuit voltage across the terminals of our network. Absolutely right. Okay, so what we're going to do is we are going to convert our circuit from the time domain into the frequency domain, find the frequency domain open circuit phasor voltage, and then convert that back into the time domain for our time domain Thevenin equivalent voltage. Okay. So what is this circuit going to look like in the frequency domain? So I need to represent all of my voltages and currents as phasors, and then all of my resistors, capacitors, and inductors as impedances. So let's start with my voltage source. Okay. So what would the phasor representation of 12 cosine 15t be? 12 angle 0. Yay, you guys haven't forgotten literally everything. 12 angle 0 degrees volts. All right, so we're good there. What should the impedance of my 10 ohm resistor be? 10 ohms, because the impedance of a resistor is just a resistor value. So I'll go ahead and I'll put a 5 ohm resistor here. What should the impedance of my inductor be? So the impedance of an inductor is j omega L. So what's omega? 15, right? So whatever thing is being multiplied by, that scrolled on me aggressively, whatever thing is being multiplied by time inside of our cosine function is omega. So we have j times 15 times 0.3. What's 15 times 0.3? 4.5. Holy mother of God. So J 4.5 ohms. Our Thevenin phasor voltage will just be the voltage drop across that J 4.5 ohm impedance in parallel with that 5 ohm impedance, right? So how might we go about solving for that voltage V Thev? So we could do nodal. I'm not going to because there's a much easier way. Okay. So you're suggesting that we do KVL around this thing. We also could do that, but I'm not going to because there's an easier way. Voltage what? Voltage division. There we go. Yes. So I see this as V Thev will be equal to 12 angle 0 degrees volts. So the impedance that we're finding the voltage drop over here is 5 ohms in parallel with J 4.5. So I'm just going to use the handy Z1 times Z2 over Z1 plus Z2 representation to find my parallel. So that's J 4.5 up here. And then the denominator of my numerator is going to be 5 plus J 4.5 ohms. Down here, I'm going to have 10 ohms plus that same thing that I have in my numerator. 5 times J 0.45 over 5 plus J 4.5. And I'm going to throw this in my calculator. Multiply that by 12. And I got 3.214 and some change. Angle 36.529. Select the 2 degrees volts. Anybody have any problem with the application of voltage division? All right. So from here, what would V Thev as a function of time be? Thank you, sir. Absolutely correct. Okay. So now we need to find our Thevenin impedance. How do we find Thevenin impedance? Or let me ask it, how do we find Thevenin resistance if this were a DC network? But we need to be looking at a live network or a dead network. Dead network, right? So we're going to combine all of our impedances together. So to turn off our voltage source, we replace it with a short circuit. Then we have our 10 ohm resistor, our J 4.5 ohm impedance for our inductor, our 5 ohm resistor, and then these are the terminals that we're looking through. So Z-Thev is just going to be 10 ohms in parallel with J 4.5 ohms in parallel with 5 ohms. So I'm going to throw that in my calculator. 1/10 plus 1/4.5 I plus 1/5. Add those together, take the reciprocal of that whole thing. And I wind up getting 2.678 and some change with an angle of 36.529 degrees. Wish my screen would stop moving on me. Ohms. And a better representation for our purposes would be to put this in rectangular form, which would be 2.152 plus J 1.594 and some change ohms. So from this, what should R Thevenin be? 2.152 ohms. What should our Thevenin inductance be? Notice that the assumption of an inductance was correct here because our reactance is positive. Okay. For what it's worth, if we only have resistors and inductors, it will always be positive. So that's the reactance, but I don't want a reactance. I want the time domain. So I need to convert that reactance back into an inductance. So if multiplying by j omega converts my inductance into an impedance, dividing by j omega should convert my impedance back into an inductance. So this is just going to be x thev over j omega. So the imaginary part of what I have stored in my calculator divided by 15i gives me 0.106 and some change. And that would be volt over amps divided by radians per second. So let's just look at the units there. So volt over amp divided by radians per second is a volt second per ampere, which is nothing more than a Henry. So 0.106. Would these values change if our frequency was different? Very much so. Our impedance would change. So for sure, the Thevenin voltage would change because that's calculated at a particular frequency and all of that kind of stuff. I would posit that the Thevenin impedance will also change at a different frequency, which will wind up giving us a different resistance and a different inductance as well. All right, we've got 15 minutes left of class. What else do we want to talk about? What do you guys not remember? I know that's an odd question to ask. So yeah, so when you say the wacky formulas, you mean the power relationships, probably. Yeah. Yep, we'll be doing that by the end of this week, early next week. So to find the Norton equivalent circuit, we could So it depends on what you mean by that specifically. So let me explain what I mean, right? So typically speaking, a Norton equivalent circuit, at least in the context of a DC circuit, would be something like this, where we would have I Norton in parallel with some resistance R Thev. Now, in our context, we might have I Norton as a phasor in parallel with some Thevenin impedance, like so, which would be fairly easy to do. We would just multiply VThev, or excuse me, divide VThev by ZThev to get I Norton, and then we would call it a day. But going back to the time domain, we have two different paths that we could take, right? So we could do something like, here's I Norton as a function of time, and then we might have some resistance R Thev in parallel with some inductance L Thev, or we could have that same Norton current as a function of time connected in parallel with a resistance in series with an inductance. Now, realistically, we already have all of the information to do the guy on the right. The one on the left is a little bit harder, but it's not ridiculously hard by any stretch of the imagination. We just need to make this R Thev in parallel with L Thev look like Z Thev effectively, right? So just for the sake of argument here, we would have R Thev times J omega L Thev over R Thev plus J omega L Thev. I could then multiply this by the complex conjugate of the denominator over the complex conjugate of the denominator. So that would look like R Thev minus J omega L Thev over R Thev minus J omega L Thev. And I'm just going to put an equal sign down here. So that's going to look like so R Thev times R Thev. So I'm going to square that. Then I'm going to have J omega L Thev. Then I'm going to have, let's see, so J times J is -1, but there's a negative sign, so that's going to turn that into positive. Omega squared L Thev squared times R Thev. Did I algebra that correctly? Let's start there. Can you guys even catch what I'm throwing at this point? I'm just trying to multiply this bit right here by this part first. So I just get a square of the resistance. And then for that second term, I'm multiplying that bit by this guy over here. So the R thev by itself comes from this bit, and then I have j omega L thev times negative j omega L thev, which I believe is positive omega squared L thev squared, because j times negative j is positive 1. Okay. So I think I did it correctly. And then down here, I would have R thev squared plus omega squared L squared. Excuse me, omega squared L thev squared. And just taking this one step further, this would look like omega squared R thev L thev squared over R thev squared plus omega squared L thev squared plus j omega R thev squared L thev over R thev squared plus omega squared L thev squared. And so we would set this equal to this guy right here. And that should allow us to calculate for a value of R and L that satisfies that. So it's much more involved if we want everything in parallel versus we just want a current source in parallel with some combination of elements, a series combination of elements. So it can be done, but it is a bit of a pain in the butt. For what it's worth, you probably won't like the sound of this. That is an impedance transformation that actually gets used in circuits 3. It's slightly less gross by the fact that we'll be doing it in the Laplace domain, where we'll be using S's instead of J omegas, but it's effectively the exact same thing. All right, so we've only got a couple of minutes left, so I think this is good enough for today. What I have on the itinerary for Wednesday, at least as far as the updated Canvas thing, is analysis of multi-frequency circuits. So we are going to talk about what happens when we excite a system at multiple frequencies simultaneously. As part of that, there will be circuit analysis going on. So if you guys can think of any particular technique you want me to look at, be it voltage division, current division, source transformation, source combination, arguably even nodal and mesh and all of that kind of good stuff in the frequency domain, just let me know on Wednesday morning and I can throw that into the example problem in some way, shape, or form. All right, see you guys on Wednesday.